Good morning. I'm Aviraj. I'm a research intern under Dr. Rahul Krishnan as well. I'm going to be talking a bit about my work over the summer on a new method for machine unlearning, specifically for selective data forgetting and also replacement. So just for a quick recap of the unlearning problem. Unlearning is the task in machine learning which is motivated primarily by privacy regulations and is the task of making a model selectively forget part of its training data, which we call the forget set. This could correspond to private, incorrect, or corrupted data that was in the training set. And the goal in unlearning is to obtain a model that was trained without the forget set and from the start, which we call the retrain model. The main question I tackled this summer was, what if we don't know what data was removed from our training set? This is what we call the data problem. In some cases, when an unlearning request is received, it's not guaranteed that we had access to the entire old training set. And perhaps we only have access to the new one, which lacks the data that was removed. And conventional methods for unlearning typically assume that they have access to this forget set to perform some level of optimization. And methods that don't assume this either don't work well, impose architecture or model restrictions, or are expensive. So our new approach is called reload. And the entire basis of this is that you can use non-identifiable information about this forget data to achieve an approximation of the retrained model. Non-identifiable information in this case refers to information about the data that cannot be used to recover or reconstruct the data itself. In our case, it's the per parameter accumulated gradients of the entire original training set, which was saved at the end of training. This method is motivated by memorization in deep neural networks and also gradient-based input saliency maps. So this figure shows the pipeline for this method, and it has three primary steps. You take the difference of the gradients on the full data set, which we stored at the end of training, with the gradients on the new training set, which is your retain set, and this gives you the gradients on the data that was removed. Using this, we divide these gradients by the gradients on the new set and take the lowest k of these parameters, the ones that have the lowest ratio, and mark them as important to the forget set. We take the lowest because it indicates that on another step of steepest descent, these parameters would be updated the least, and thus they know the most about the data we want to get rid of. Once this is done, we use these same stored gradients to perform a priming step of ascent, reversing the last step of training before reinitializing the important weights and then training on your retain set to achieve whatever performance you wanted at the end and give you an unlearned model. Throughout the summer, I explored multiple methods of identifying salient weights. What I described earlier was lowest proportional magnitude based. I also explored using lowest magnitude based without the division, which had slightly worse performance. Highest magnitude based, which exists in prior work but caused model collapse. I used some second order methods such as the Fisher information matrix, which works in some didn't work as well, and also used a Hessian approximation inspired by the optimal brain search and constraint problem, which was memory intensive and also offered subpar results. I then carried out an empirical evaluation of this method on three conventional unlearning tasks, randomly forgetting 10%, 20%, and 30% of the original training data across 4 data sets, 2 model architectures, and 10 random seeds. The results for this were pretty good. In comparison to the retrained model, on average, we have less than a 1% difference in accuracy on the forget set, implying that this unlearned model behaves extremely similarly to the one that had been retrained without the forgotten data from scratch. Additionally, it attains really good downstream performance on the retain set, showing that it's still a useful model, and most notably, reliably defends within a 1% success rate from the retrained model on membership inference attacks, which means that it's very good on protecting user privacy. Finally, the symmetric KL divergence of the model produced by reload in comparison to the retrained model on the forget data was also extremely low, showing that they have produced similar logic distribution. Upon the recommendation of Dr. Krishnan, I also carried out a few additional studies on this method. I attempted to use multiple gradient descent steps before reinitializing, just to see if there's more signal, and this had no significant gain in performance. I tried using a student-teacher setup for retraining instead of the classical setup, but this allowed the unlearn model to recover information about the forget set implicitly from its teacher, which was the original model. And then I also tried using the Fisher information matrix and Hessians to perform natural gradient descent and also descent for retraining, which gave no noticeable performance gain and increased computational overhead. But using a 2D synthetic dataset, I also then studied how this method modifies the decision boundary of a classification model. Typically, reload, my method, does change the decision boundary of the original model and brings it much closer to the retrained model. We also found that it differs only mostly in the places where there are few or no data points in the dataset. An inherent weakness of this method, is one that you have to store gradients, which means that there is a memory component, and also that it does tend to fail when the forget set has very similar or exact duplicates it's still existing in the retain set. And I believe this to be an inherent limitation of the method, just given the nature of the importance calculation. This brings me to selective data replacement. So unlearning deals with forgetting data, but in some cases we want to replace it with new data. For example, if we want to hide sensitive information, correct part of the data, improve some of the quality of it, correct mislabeled data, or remove backdoors that exist in the training data. And we consider this an extension of the unlearning problem. This is the same figure as before, but slightly modified. And here you can see, instead of just looking at the gradients on the forget set divided by the gradients on the retain set, we've got the difference in the gradient between the original data set and the new data set to get gradients that identify the difference between the two. The rest of the figure is the same. For this task, I also carried out an empirical evaluation, and I'm still in the process of doing so as well. So the tasks that we tested on here were replacing data that was 40% noise, correcting labels for 10% of the data that was mislabeled through a label flip attack, removing patterned backdoors from 10% of the data, or updating and correcting information in tabular data. Those last two are still in progress. This was across 3 different data sets and 2 different model architectures. The results for the completed tasks show that through reload, we effectively get improved accuracy on your actual testing and retain and new data set. This shows that any sort of performance degradation that was caused by the corrupted or mislabeled data is corrected through this method, through a jump of almost 10% in noise replacement and 15% in correcting mislabeling. The next steps I have for this method are testing on generative models, such as forgetting and replacing the generative capacity of stable diffusion and other diffusion-based methods, image generation methods, and also forgetting knowledge from LLMs and replacing sequences of tokens that they generate with new ones. And as mentioned before, updating tabular data and removing backdoors. Thank you. I'd like to specifically thank Dr. Rahul Krishnan and everyone in the group for the help, discussion, and company. Thank you.
And great work, amazing, and really in trend in terms of privacy and all regulations in Europe and Canada as well. I was wondering if you had an opportunity to work on real use cases like healthcare data or something, or you're willing to do that?
That's a fantastic question. Yes, I currently have plans to go and test this on some actual healthcare data, specifically in this case for updating and correcting information in tabular data, because I feel like as methods progress or as a doctor becomes more familiar with a patient, some of the information about their medical status may change, and thus we don't want to retrain a model that knows that about them. So I've got some data sets planned for that. I don't know them off the top of my head, but I have a list. Yeah.
Amazing, amazing work.
Thank you.
Patrick.
Yes, Patrick.
You showed a figure how reload fares between the retrained model and the original model. We had these like 3 something. Yes.
This one?
I know, like the next one. Yes.
Yes.
Could you please explain about the 3 different?
Yes. Sorry. Yes. Okay. I didn't realize it wouldn't be visible. But so this So these are all the same decision boundaries plotted here.
Mhm.
However, this first one contains the data points that are in your forget set. The second one contains the data points that are retained. And the third one is the full data set, so all of them. So it's just an easy way to see where everything falls before and after unlearning.
Thank you very much.